Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all of you. Today I am going to deliver a lecture on static, and under this topic you will learn about forces and torques in equilibrium. So before we move further, let's talk about static. What does it mean by static? Static is at rest or stationary. Some also say not moving. Whatever it is, you must know that static is the science dealing with the forces that produce balance in stationary object. So in this chapter, our discussion will focus on the investigation of non-moving object. Okay? So what does it mean by equilibrium? So equilibrium means in a balanced state, or some also say steady, or undisturbed, or unmovable. Okay, wherever it fits the context. It is depicted everywhere in our surroundings. For example, our houses, right? So the houses we live in, the tall buildings in our townships, the bridges across rivers and highways, and many others. Would you imagine what will it be like if there is no equilibrium? It will be very difficult, right? So in general, we must say that equilibrium is very important in our physical nature and daily life. So in the field of aeronautical, okay, forces and torques in equilibrium is applied in order for them to design, okay, the aircraft. And in architecture, of course, okay, they need to learn about the structural and the stability of the buildings. And then forces in muscles, bones, and joints for biomedical, whether is it in medicine or in biomedical engineering. For industrial technology, okay, they need to apply this topic to learn about stability of cars and strengths of materials for other engineering field. Okay, let us talk about one basic example of static equilibrium. So this is a man standing, and as you can see from the free body diagram, the normal force is equals to the weight of the stationary person. That makes the net equals to 0. The net force equals to 0. For a rigid body to be in equilibrium, it must satisfy two conditions. Okay, but before that, what is rigid body? So rigid body is a body with a definite shape that doesn't change, so that the particles composing it stay in fixed positions relative to one another. So first condition of equilibrium, static equilibrium, is the net external force must equals to 0. So sigma F equals to 0. And you know that the force also can be in terms of component X, which is also equals to 0, and the component Y equals to 0 as well. This is a necessary condition to ensure that an object is in complete mechanical equilibrium. So the second condition of equilibrium is something to do with torque. Okay, the second condition of equilibrium states that the net external torque must equals to 0. Okay, so torque equals to 0 about any point. Right? Torque is the tendency of a force to rotate an object about some axis. And what is the basic equation of torque? So you have learned this before in your previous lecture. So torque equals to F times R, which is equals to F d sine theta. So the R is lever arm. The value of torque depends on the axis of rotation, right? And what is the unit of torque? Okay, the unit of torque is Newton meter. And the direction of torque. Okay, the direction of torque is very crucial as well, because for clockwise it is negative, or counterclockwise it is denoted as positive, right? So equilibrium is considered as two cases. Okay, one is static equilibrium that we are actually discussing right now, a particle at rest and not accelerating, and another equilibrium is dynamic equilibrium. Okay, so this one is not in your syllabus. A particle moving relative to us and not accelerating. So we are just focusing on this static equilibrium. So a zero net torque does not mean the absence of rotational motion. Okay, you must remember that. And an object that rotates at uniform angular velocity can be under the influence of a zero net torque. So alpha equals to 0. That means no rotational acceleration. So torque equals to the I times alpha. That will be equals to 0. So this is analogous to the translational situation where a zero net force does not mean the object is not in motion. So A equals to 0, object in translational equilibrium. So F equals to MA will be equals to 0. And this is also you have learned from your previous lecture, I believe, right? So torque, again, we discuss about torque here. So to make an object start rotating, a force is needed. Okay, you must apply a force in the system. So the perpendicular distance from the axis of rotation to the line along which the force acts is called the lever arm. So for the case of the FB here, okay, the lever arm is this one, RB. And for the case of FA here is RA. Okay, this one is a very basic concept of torque. And what happened for another angle? Alright, so here the lever arm for FA is the distance from the knob to the hinge. So if you see this FA, the distance from the knob to the hinge is this one, right? So from this to this, right? So the lever arm for FD is 0 here, right? And the lever arm for FC, this part, is as shown down here. You can see. So this is FC. Alright, so the RC is this part. And you can analyze the equation using sine theta equals to RC divided by D. This RC divided by this part. And you get actually the RC equals to sine theta times D, or equals to D sine theta. So that means the torque is FC times the RC equals to FD sine theta. So this one is also something to do with torque. So torque again is equals to F times R equals to FD sine theta. And from this diagram you can see that a longer lever arm is very helpful in rotating objects. You can see here, right? So if you put your hand here, okay, it will be a bit difficult for you to use this tools, okay? And same goes with the wrench. Okay, I really hope that you guys can follow the lecture and we will continue our lecture again next time. Thank you.